I'll try to finish by noon, which is 40 minutes away. And I think that's possible because this part is so much more straightforward in comparison with the earlier ones. So now we're going to talk about the rationale of the MPW strategy. And I hope you will find it to be very intuitive. So before the lunch, I'll talk about the rationale. And after that, we'll look at implementation. So we have shown the 4 columns, right, that correspond to these 4 potential outcomes. 2 of them, at least this can be observed from every control unit. This can be observed from every experimental unit, but we understand they are counterfactual for the people who were not in that condition. Y1 M0 looks like a counterfactual for everybody, for every treated unit. And the Y0 M1, for the control unit, but we don't observe this probably directly for each control unit. So these are purely counterfactual, and these are at least 50% counterfactual. So how do we estimate each of these? First question, identify. These are population average counterfactual outcomes. Now, can we relate all those things that we don't know or we probably won't observe, relate them to the observable information, right? So that's a question about identification. And so what I did was, the reason we focus on those 4 terms, 4 expectations, because we have shown the direct effect, and we use the term natural direct effect, is the contrast of the first and the third. This is the indirect effect in the conventional term, but in post terminology, this is the natural indirect effect, is a contrast between the 2 middle terms. And this is a pure indirect effect, right? It's the indirect effect when everybody is untreated, and it's the contrast between the first and the last term. That's using Robbins and Greenland terminology. And then finally, we have that interaction term, which involves all 4. Right, because you're subtracting the pure indirect effect from the total indirect effect. The difference is the natural treatment by mediated interaction effect. So if we can identify each of them separately and then just do the mean contrasts, will be all done. And that's exactly our goal. And then follow the same logic as marginal structural models. Remember, when talking marginal structural models, when you evaluate, a treatment in contrast with the control condition, the 2 groups are different. But your goal is to say, if everybody is treated, what will be the average outcome? Right? So if I can make my treated group look like the entire population through weighting, then the weighted mean of the treatment group identifies the population average outcome when everybody is treated. Does that make sense? If your treated group has the same composition as the entire population, right? Through weighting. Now, randomization guarantees that, in expectation, your treated group has the same composition as the entire population. Therefore, if you have randomization, you don't need a weighting. You just take the mean of the treated group, identifies the population average outcome when everybody is treated. But if you don't have randomization, weighting helps. If you have ignorability assumption, if your weighting takes care of everything that that has to do with selection bias that makes your treatment group looks different from the population. Through weighting, you adjust for that difference. And your goal is to estimate the population average potential outcome when everybody is treated. And then you put that aside, and then you go work with the control group. You say, now, how does my control group look different from the entire population? In which ways are they different? And I'm going to remove that difference through weighting again. So I'm doing exactly the same idea here. And I'm saying, this one, it's easy to identify if treatment was randomized. And this one is easy to identify if, again, the treatment is randomized. But if treatment is not randomized, I use the idea of marginal structural models, right? I find out how each treated group and the control group is different from the population, and I use weighting to change their composition. Now, these ones requires additional adjustment to take care of the mediator value selection, and which I'm going to show how we adjust it through weighting in a second. But the goal is, now I'm saying, if everybody was treated, but their mediator takes value as it would under the control condition, and if I find out this kind of factor for every individual and then average over the population, I have this average, right? And this is my goal. I want to identify this quantity. And after I take care of that, I want to identify this quantity, one at a time. If I can identify one at a time, then I do mean contrast at the end. So that's where we are going. So how to identify this counterfactual? So this is an illustration. And it starts with the notion that identification is so much easier if you can design a randomized experiment. That's this guy said earlier. Is that you said if we can randomize treatment and then within each treatment condition we can randomize the mediator, and then we can identify those what we call the controlled effects, and it also helps you to identify these indirect direct effects as well. And except because we're decomposing the total effect. So you have to be aware, how is the treatment affect your mediator? How the employment rate in this case has been changed by the treatment. And that has implications for your second stage randomization. Because when you randomize mediator values in each treatment, you don't use the same probability, right? If you randomize people to treated or control with probability 0.5 under each treatment, you are not capturing the treatment impact on the mediator. Because the fact is the treatment changed your probability of being employed. So if all these people are identical, if you assign it to the treated group, we know the employment rate is going to become 65%, so the probability should be 0.65 if you do randomization, right? And in the control group, the employment rate is 0.4. So the probability of mediator value assumption should be 0.4 as well. So you differentiate these probabilities when you randomize the mediator value to reflect the treatment impact on the mediator. And if these people are identical, which is a huge assumption, using this kind of sequential randomized experiment, you will be able to identify these things. So we'll go with this logic for now, and then we'll see with this randomized experiment, and the weighting will come so handy to identify these counterfactuals. So I started with the treated group. I'm using some rounded up numbers. Let's say under the control condition, 40% people will be employed. And so when I do randomization, I randomize 40% of the control units to be employed and 60% to be unemployed, right? And after this second stage randomized, of course, people have been randomized to the control condition first, then they're randomized to be employed or unemployed with this probability. And then you can observe the outcome of each individual and take an average of the controlled outcome of all the control units. It identifies this quantity, right? This is, the population average when everybody is untreated. Since you randomize the treatment assignment, of course, the treated outcome, the observed outcome of the treated units on average identifies this. Except I spelled out how the treatment would affect the mediator here, and use that to randomize, using the probability of mediator value assignment that reflects how people responded to the control condition. And the people would respond to the treated condition differently. Again, these are the people who are randomly assigned to the treated group. But in the treated group, let's say employment rate will be 0.7. Suppose the welfare office has jobs enough to serve 70% of the applicants. And then we randomly assign those 70% of people to the treated condition, right? And then you observe their outcome and take the average and identifies the average potential outcome when everybody is treated. And these identifications are straightforward. What they all require is the random treatment assignment. So now we are working on the last one, right? Suppose everybody is treated and the mediator is M0. How do you identify this quantity? So I'm saying, I cannot use this one because here everybody is untreated. I cannot use this one because here the employment rate is 0.7, while if under the control condition, the employment should be of M0 should be 0.4. So that's the issue. The randomization, the second stage randomization helps because not just the treated group and the control group on average are comparable. Also within each group, the employed people and the unemployed people are comparable. That's the beauty of sequential randomization. The problem is I need the employment rate to be 0.4 rather than 0.7 in the treated group. If I can change the employment rate in the treated group, reduce it to 0.4 from 0.7, and then I take an average, I'll have this thing. Right? So how do we make that happen? And I hope your light bulb shines up in your mind saying, well, why don't we weight it? Yeah, let's weight the employed people. I don't need as many as 70%. I want them to represent 40%. So you downweight them, right? So every person doesn't represent an entire person. It represents a portion of a person. That's how you downweight. And correspondingly, I want 60% of people to be unemployed rather than 30%. So I want these 30% of unemployed people in the treated group to represent 60%. So I give them a weight greater than 1, of course. I want each one of them to represent 2 people. That's how you increase the percentage unemployment rate from 30% to 60%. So it becomes obvious what the weight should be. What kind of weight you would use to make that transformation, right? So everybody who is employed in the treated group receive a weight 4/7. And everybody who is unemployed in the treated group receive a weight equal to 2. That's very straightforward, right? Then all of a sudden, the transformation is done. And then remember, the employed people and unemployed people, because of the second stage randomization, they are comparable. So weighting doesn't change the comparability. It just changes the relative representation, the relative proportions. Now it gives you the proportion, the distribution you need. Now it gives you the distribution M0 in replacement of the distribution M1. So that's how, that's the essence, that's the core of this idea. And now I write the general form of the weight, right? So under sequential randomization, the numerator of the weight is simply the proportion of people who are in a certain employment category in a control group. So if you're employed, that's if you're employed, the numerator is 0.4, right? And if you're unemployed, the numerator is 0.6. And the denominator is the corresponding probability in the treated group, right? And so it's 0.7 if you're employed, 0.3 if you're unemployed. So that's the general form. And I can use theta M0 in the numerator and theta M1 in the denominator. Theta is just for this, represents this conditional probability. So I think, that's it. We can just end here and you know how to do the rest, I hope. So now how to implement, once, like I said, once you identify, this is just, the third counterfactual outcome. And then you're going to apply the same logic to the fourth potential outcome, exactly the same idea, and then you can be innovative in working out what the weight needs to be. And that's a small exercise for you. So now what you need to do is just contrast these means, right? And each of them now become identified with observable information, and then you just take the mean contrast that gives you the causal effect that you wanted. So I started with, here's one way of implementing it. And so I started with my first column was a control group. When it's unweighted, it identifies this quantity, the average control mean, right, in the population. Here is actually the third column you just saw. This is the third column. I take the treated group, although I weighted. This is the weight we just worked out. And after weighted, I got this counterfactual outcome on average, right? And then I contrast these two. If you don't weight it, the contrast gives you ITT effect. If you weight it, the contrast gives you the direct effect. The direct effect, when you change treatment from 0 to 1, the median stays at M0. So that's mean contrast. And you can just work out these two mean contrasts and say, wow, I got a direct effect. And what about indirect effect? Okay, so this is the middle column I had, which has the treated group. But in this case, unweighted. When it's unweighted, everybody has a weight equal to 1, right? You just represent the entirety of yourself. And that average identifies this one. It's the unweighted treated group. Their average outcome identifies the average outcome in the population when everybody is treated. And so if you contrast the weighted outcome of the treated group and the unweighted outcome of the treated group, that contrast gives you the indirect effect. That makes sense, right? So the only trick is I'm using the experimental group a second time. At one time I didn't weight it, and another time I weighted. Right? The difference between weighted and unweighted gives you indirect effect. And the difference between the weighted treated group and the control group gives you the direct effect, as we saw earlier. So that's it. And whether you use regression or not, it doesn't matter. And I'm going to show you a regression model just for convenience. And of course, you can estimate each quantity separately, but the regression gives you some standard error, even though the standard error is somewhat problematic, which I'm going to touch upon. But at least it gives you the point estimates, which should be consistent if your ignorability assumption is correct. Now, if you actually had the kind of sequential randomization as we just described, then the results will be unbiased. So the weighted outcome model, I write it this way to create these mean contrasts. So basically, I put in white to regress on the treatment and a duplicate indicator. So I have the treated group used twice, right? So the duplicate indicates that the first time I use the weighted version, I use the original. The second time I use the unweighted version of the treated group, I create a duplicate for that purpose, right? So that's a duplicate indicator. So when D1 equals 0, I'm contrasting the treated group with a weighted control group. I got this contrast. That's a direct effect, and that's gamma DE. That's coefficient for T, because T is the variable that changes when D1 stays the same. The second time, when T stays the same, but I change D1 from 0 to 1, I got a second contrast. So the coefficient for D1 is the indirect effect. So this is just a regression trick for getting the mean contrast that I'm interested in. It's no different from taking this contrast first, then take this contrast, and they add up to the total. So this is straightforward, right? Of course, so each causal effect is a single parameter. That's one thing I love is you don't have the product of anything or sum or product in a multiplicative form in complex ways. But here, every causal effect is a single parameter. And you hope that if the standard error is right, the estimation is so straightforward. You can do this through, it's a weighted outcome model. You can do this through weighted least squares. Alternatively, you can do weighted method moments. In the method moments, it's used a lot by economists. And it really comes handy because all we are doing is the simplest method moments estimation. And we're using the first moment, which is the mean of each group, weighted or unweighted. So now, coming back to the design we have where only the treatment was randomized. We only have randomization treatment. The mediated value was not randomized. And instead, we rely on the ignorability assumption. The first ignorability is straightforward. The second ignorability heavily depends on, completely relies on whether you have covariates that helps you to distinguish people who are more likely to be employed from those who are less likely. And so we need to assume sequential randomization now within levels of X. Within levels of X are people who share the same background, same pre-treatment information, such that the fact that some of those are employed, some are employed, is due to whatever haphazard events happening in the real world on a daily basis. So now within levels of X, now we do the hypothetical sequential randomization in your mind. It's a thought experiment for people who are identical in their covariate, right? And among the people who are identical in their background, we sequentially randomize them to treatment and then to mediated values. And then we apply this weight. We apply this weight to the employed people in the treated group, and then we apply this weight to the unemployed people in the treated group. Everything, the weight looks just like before, except now I'm conditioning on X. Right? So in other words, I'm doing the sequential randomization in subpopulations of people who share the same pre-treatment background. So now it's still theta M0 over theta M1, but each theta is a function of X. And so each theta is the probability of your actual mediated value given the treatment that you were assigned to or would have been assigned to, and given your covariates. So those are the propensity scores. And assume everybody knows propensity score, right? Sean, is that right? Everybody knows propensity score in this class? Even if you don't use it, you have seen this form. So now we got that comes the ratio of two propensity scores, right? And every propensity score is a probability. It's a conditional probability. So that's why I'm going to call it the ratio of mediated probabilities, right? It's propensity for a certain mediated value given a certain treatment condition. So now, like I said, why should I believe in your ignorability? There's every reason to challenge it. After you have examined the covariates that have been considered. So here's a set of covariates we have having measured in a new study. Most importantly for us, because we're looking at the psychological well-being at the end of this 2-year follow-up. So we have included psychological well-being at the time of randomization, the baseline depression scores. We have personal history of employment history. We have personal history of employment and history of welfare dependence. We have their human capital means, their education background, their employment status at the baseline, their earnings, income at the time of randomization, and their self-reported at the baseline preference to work, willingness to accept a low-wage job, ashamed to be on welfare, perceived social support, perceived barriers to work, and so on and so forth. And household composition, other personal conditions, whether they have family burden, have health issues of themselves or family members, et cetera, et cetera. So we think that the study did a very good job collecting all the information that it should be predictive of how likely one would be employed. And also, should be predictive of how depressed they would be under one condition or another. And given this list, then you ask yourself, let's scrutinize the ignorability assumption and think about what could be some omitted confounders here and how important those confounders would be. And if they are omitted, should you take them into account how different the result would be? So that's the thought process you have to go through, and you have to go through this on scientific ground. So this is crucial, like I said, for the identification assumptions. And the key identification assumptions we rely on with this method, the same is true with most of the other methods, except for the IV, is we rely on sequential ignorability. In this case, the treatment is already randomized, but we do have to assume that within levels of pre-treatment covariates that we have observed, there's a sequential randomization, right? Such that there's no confounding of treatment-mediated relationship, there's no confounding of treatment outcome relationship, and more importantly, there's no confounding mediated outcome relationship within a treatment and across treatments, right? And the latter implies that there's no post-treatment confounding. Not just there's no pre-treatment confounders but left out, but also there were absolutely no post-treatment confounders conditioning on the pre-treatment confounders. So among people who share the same pre-treatment information, there's no such thing that could have been affected by the treatment that will confound the mediated outcome relationship. And I'll give you an example of the immediate depression level after the treatment assignment. That's a potential post-treatment confounder. And as I mentioned, if there's a treatment by mediated interaction, none of these methods I have, reviewed so far could handle a post-treatment confounder even if it has been observed. And this method couldn't either. Unless, if it has been observed, we can include it in as a second mediator, and we can find, just extend this weighting method to decompose the total effect into multiple pathways. But if it's unobserved, there's nothing you can do about it. But the nice thing, pretty much that's the only thing we have to assume. And the outcome model cannot be simpler than this, right? You don't need the covariates in there at all. You could put them in if you want. It will reduce the standard error, but it's not essential. You don't rely on putting in the covariates here to remove any confounding. Therefore, there's no risk involved in the outcome model specification, right? So really the key assumption is sequential ignorability. Of course, you would say you do have propensity score models that you have to specify, right? What if your propensity models were wrongly specified? Would there be a consequence? The answer is yes. And yes, in particular, if you use the propensity scores as estimated. But I will show you an alternative, which is to estimate the weight non-parametrically. And I'll show you that the result could be a lot more robust, even if the propensity score model was misspecified. So there is some way to circumvent it. So in general, we dramatically reduce the reliance on model specification. And importantly, we don't have to assume that interaction doesn't exist, and which is crucial when interaction could play an important role, as we have here in this case. And we don't assume the exclusion restriction. And like I mentioned, the outcome model really is very trivial. So now it's time for you to think about how to identify the other counterfactual average outcome, y0, m1, by applying the same logic. And I've shown you the treated group and the control group here. And now we want to have this term identified. In other words, we want to take the control group, but we want the control group to have an employment rate the same as you would see in the treated group. We want 70% people in the control group to be employed and 30% unemployed. What would be the weight you use in this case? And it's in your handout. I asked you to fill out the blanks here. And I'm sure you can get it done in 1 minute. And of course, exchange ideas with peers may help as well. So you write out the weight for the employed people in the control group, the unemployed people in the control group, and then you write down the general form of the weight down here in this box. Please raise your hand if you have already got a solution. You guys have done? Would you mind write it on the whiteboard down back there? So the first one is 7/4. The second one is a half. And the general form is, what is theta? Would you mind? Yeah, define for us what each theta is. By the way, we're assuming that there was a sequential randomization. So you don't have to worry about x at this point. Thanks so much. Please take a look. And did anyone have a different answer? Did you have an answer different from what she just wrote? On the right side, in the right column of the whiteboard. The general form that she wrote down is omega equals theta m1 over theta m0, right? Theta m1 is the probability of the mediator given t equals 1. Theta m0 is the probability of mediator given t equals 0. And that's the weight for people whose mediator equals little m, right, in the control group. Did anyone have a different answer? All agreed? So you all get 100 points. And from now on, you can invent your weight in every new scenario. So that's why I think it's really straightforward once you understand the logic. So now we put in this fourth potential outcome that you just figure out how to identify. You identify that by bringing in the control group again, right? The second time. But this time we're going to weight it with the weight that you just wrote down. And the weighted observed outcome of the control group identifies this quantity, y0, m1 on average, to be contrasted with the unweighted outcome of the control group that gives you the pure indirect effect, right? This is how the policy-induced change in the mediator would affect your depression if everybody was untreated. And then we expect this contrast, remember, to be close to 0. Unlike the direct effect. Remember, this contrast was the natural direct effect or the total direct effect. Sorry. Yeah, so we have the pure indirect effect and the total indirect effect comes from the contrast between the weighted and unweighted experimental group mean. Right? The weighted and unweighted control group mean gives you the pure indirect effect, and then the difference in difference is the interaction effect, the natural trivial mediated interaction effect. So I just play the trick with the regression again to get this last contrast that we were interested in. I created another column called a D0. D0 is we had a D1 right earlier, indicating whether a treated unit is weighted or unweighted. 0 if weighted, 1 if unweighted. Now I'm using the control group twice. So I create another duplicate called D0. And this time, 0 is unweighted, 1 is weighted. It's just little tricks to get what I want. So now D0 has a coefficient corresponds to the pure indirect effect. And then I have the total indirect effect here and the pure indirect effect here. I take the difference. The difference identifies this interaction effect, which is natural. So that's pretty much it. And more to follow on estimation in the afternoon. We're going to talk about weighted least squares, which is equivalent to weighted method of moments analysis, as I mentioned. This is tricky. This is the issue has to do with estimating standard errors. just like any causal inference that involves propensity scores, it typically comes in 2 steps, right? The first step is to estimate the propensity score. And then the second step is to use it to reduce selection bias in estimating the causal effect. So that's called a 2-step estimation problem. And it's a problem because if in your second step, you assume your propensity score is the true score, you're ignoring the estimation error in the propensity score, you're going to have a biased estimate of the standard error. So it could affect your statistical inference. So this 2-step estimation complicates the estimation of standard errors. And this is something we're going to take care of with great care, which I'm going to mention in the afternoon. I think it's time for lunch break, and we cannot believe that.